All right, so what we're going to be looking at today is I'm going to be introducing to you some concepts related to gas laws. So up through now, we've been kind of talking about gases in a way that we've seen what they can do in respiration, we've seen what they can do in photosynthesis, right? We've talked about them briefly when we've looked at chemical reactions, we've looked at how matter can interact. But we kind of are saving gases to their own unique time to discuss because gases are going to behave a little bit differently than other things that we've looked at in regards to matter. We've been looking at solids, we've been looking at liquids, but gases, because of their broad, expansive nature, is really kind of the best way to describe it, is they're going to behave a little bit differently than what we've seen with other types of matter. And so what we're going to do is talk about gases a little bit to give us some context about how they interact, how they play together, how they respond to different reactions, and what they can then later do to an ecosystem as we begin shifting into talking about greenhouse gases. Okay, so this video is just really kind of introducing us to some major kind of what a gas can do, how it behaves, and to set us up for looking at and observing how gases behave in different scenarios. Right? So what makes kind of the following three things really function, right? If you're thinking about what they do and how they interact, they're all based on how gases are functioning. So like a hot air balloon floating, right? Soda spraying all over you after you open it, right? Your lungs filling with air, right? We talked about how different gases can move through those different areas, but keep those things in mind as we think about how gases are behaving. So let's define what gases are. So these things that we address, those four things, are all due to the behavior of how the behavior of gases and what they do and how they function. So just remember, a gas is a state of matter, right? If we're talking about a piece of matter in a particular gaseous state, it's because that has transitioned from a solid to a liquid or a liquid to a gas. Right? So a gas, again, is just a state of matter in which we define it as its ability to not only fill the shape of the container, but to take up the entire volume of it. So they will mold to it. So that's different than what we see when we're looking at a solid, right? Solids have a definite shape and a definite volume because they're contained and they can be molded. Liquids have a definite volume, right? So ever how much you actually have, but the shape of it will take the shape of the container. Right, that's different than what we're seeing with gases, where gases will fill up the entire volume of the container and will take the shape of that container. There's some other things to be thinking about with gases too that'll come into play as we begin to look at the relationships of different variables and different settings of what they can do. So is that one, that gases are going to behave due to random motion, right? As they move around a container, they're going to bounce and collide and they're going to continue to move. And how often those interactions occur will define and explain a little bit about how that gas will behave. Okay. The other thing to think about gases is that generally gases aren't really attracted to each other. They don't have very strong intermolecular forces, right? They either have a lot of energy, which allows them to kind of spread out, or they're structured in a way where those electrons and protons don't really want to interact with each other and they'll kind of stay apart and stay away from each other. Okay. They function as fluids. So again, a fluid is anything that flows or moves. So in this case, like a liquid or a gas, right? They are going to fit this shape of the container. So keep that in mind. I might refer to the fluid motion of gases, and that's because they are fluids. And generally with gases, there's low density. That means that there's not a lot of matter in a particular volume. So like all matter, gases will interact with each other as the different materials collide. So if we think all the way back to when we talked about Newtonian physics and we talked about forces, right? Anytime we had two objects interacting with each other, we had a force generated, right? Where one object was pushing the other, and that was dependent upon the mass of the object and the velocity of the object. So, or the acceleration of the object when we look at F equals ma. Okay. Here we're still looking at that same concept, but we're looking at how these different materials interact with each other. So for example, solids have lots of collisions because they're very tightly impacted to each other, but they have very low energy, right? So those forces, right, as they push and pull against each other, they're relatively weak. Liquids, they generally can move a little bit faster. Either they have weaker molecular forces, which allow them to move a little bit more, right? And they have generally more collisions because of the fluid nature of the flowing of the material. Then you have gases where you don't have very many collisions because they want to spread out, but you generally have more energy in them, okay? And that will come into play a little bit. So there's a scale that we'll look at as we start talking about different pieces of matter. So just to remind you what an intermolecular force is, and we'll talk about them a little bit, is that an intermolecular force is the forces of the particles inside of different molecules interacting with each other. So is that they're going to be attracted to different parts of the atom or due to different bonds that are in the atom because of how the electrons and protons are oriented around the different material. So the one that we're really interested in when we're talking about gases, specifically the ones that we're going to be focusing on, are London forces, or you might remember them as van der Waals forces. It's that you have materials interacting weakly because of just the random movement of electrons around the nucleus of the atoms inside of the molecules. So there are times when they interact with each other where maybe there's fewer electrons as they're getting pulled to one side of the atom than the other, where they'll stick together a little bit, but then once they collide, they'll push each other apart. That doesn't mean to say that there aren't other intermolecular forces that are happening, like hydrogen bonds, that could attract or force or push or pull different things. Or you might have even stronger ones, but for our purposes, we're going to keep it kind of onto assuming that it's very weak bonds happening between the different materials. Okay. So with this, IMFs play a role in the nature and how they behave. And the higher the energy they contain, the less those intermolecular forces are going to, not say interact, but affect it, right? The more energy you have, the easier it is for these particles to move apart. Okay. Also have to think about the size of the container. The larger the container is, the less interaction those materials are going to be. Think about you inside of a giant concert hall. If it's just you and one other person, chances are you're not going to be interacting with each other. But if it's completely full, there's going to be people bumping into each other, right, as you're trying to get to your place, like say at a concert. Okay. So when we're talking about gases, we're going to be dependent upon through 4 different things, right? These are the 4 things that we're going to talk about and how they interact with each other through this short unit, right? Is that we're going to talk about pressure, we're going to talk about volume, we're going to talk about temperature, and lastly, we're going to talk about how the amount of the material can affect how the gas is going to behave. Okay. So pressure. We defined pressure a while ago when we were talking about gas exchange inside of your lungs. Right? We defined pressure as the force of the gas that's exerted on the container which it's in, right? And that the pressure is dependent upon not only the volume, but the amount of the material that's there, right? The higher the material you have within a contained area, like say when you're taking oxygen into your lungs, that's going to affect how different materials are going to move. So again, as materials are moving inside of this, and when I say materials, gases collide inside of a container, the forces that exchange are due to these elastic collisions, and that's going to dissipate and spread energy throughout a particular area, because again, we know that energy and force are linked to each other. Okay, so again, the more collisions that you're going to have within a material, the greater the pressure is going to be. So when we're talking about pressure, again, we're talking about the relationship of force over the area. So when we're talking about our basic unit for force, we talk about a Pascal, or in our purposes, a kilopascal, which equals to a Newton per meter squared. Okay, so essentially how much force you're applying on a defined volume, or sorry, a defined area. So like if you were, say, pushing against the wall, that's the force that you're pushing on that wall, and the pressure there is going to be greater than, say, the other areas of the wall, because that's where you're going to be hitting it. So here I have listed a bunch of different conversions for different pressure ranges, so different ways you can measure pressure. So one that we're going to be using a lot is called an atmosphere, or an ATM. And an atmosphere is just kind of the general one that we use when we're talking about like weather, right? Oftentimes you'll see that. You'll also see other measurements such as millimeter of mercury, or torr, or pounds per square inch, or PSI, like what's in your tire. Okay, that's what you measure pressure in your tire is. But again, all of these are measures of some kind of force over a particular area. Okay, and so we'll talk about what that means when we're looking at some different relationships and as we're trying to calculate what we might expect given particular volumes or values of pressure, okay, and what those mean. Another thing we'll think about is volume. So volume, again, is the space in which the gas is contained, and we measure that in, say, meters cubed or in liters, and there are other measures for volume that you could utilize. So again, what's the role of volume? So as we know, gases are materials that will fill the size or the shape of the container. So the larger the container is, right, the more we're going to have some kind of effect on the relationship of the gases interacting with the collision. So again, the larger the container is, the less the collisions are going to affect it, versus if you have a very, very small container, right, things are going to bump into each other more quickly or more often. So the last thing that we're going to look at is, or another thing we're going to talk about is temperature. And so we've talked about temperature when we talked about heat, right? And that temperature is a measurement of thermal energy. So what does this mean for a particle that's having this increase or decrease in energy? And we know that temperature, essentially what it's going to do is that it's a measure or gauge of how much energy the particle contains. So the more energy that you put in the particle, right, the faster it's going to be able to move, the more often then you're going to have collisions between the material because it's going to be moving faster. Okay, so it affects how often the particles in the material are going to interact with each other, as well as with the side of the container or whatever it is. And so think about what could that do for pressure. Okay? And we can measure temperature in 2 ways. Generally, we're going to be measuring temperature in the scale of Kelvin, or you're going to be given Celsius, you might have to change it to Kelvin. So lastly, the other thing that we need to keep in mind is the amount of material that we're actually dealing with. So the amount of material is going to affect how temperature, volume, and pressure are going to interact. Okay, and we're going to be measuring gas amounts both in moles as well as with mass, where we're looking at kilograms. Okay, so we're going to be changing back and forth with that. So that's our basic introduction to gas laws, right? It's not a whole lot of stuff that I want you to look at now. I just want you to be thinking about those different things, to be thinking about the relationship of gases, to be thinking about the relationship of gases between pressure, gases with volume, and gases with temperature. Okay. So what I want you to do to think about this and help prepare for what you're going to observe is that using your knowledge of these different relationships, thinking about, okay, if I'm really thinking about what's happening with pressure, if I'm really thinking about what's happening with temperature, if I'm really thinking about what's happening with volume, how are these different things going to relate to each other? So for example, I want you to write down the relationship that you think is going to happen between pressure and temperature, right? So just those two variables. So what's going to happen to temperature if, say, you change the pressure? What's going to happen to temperature if you say change the volume of your container? And then what's going to happen to the volume if you say increase or decrease the pressure? So I want you to write out, like in sentence form, what that relationship is. And do this on something so you can turn it into me so that we can then discuss what the relationships are going to mean for that particular piece of material. All right, so that's it for the introduction to gas laws. So again, remember, gases are particles that are moving around in containers, right? That they have energy, and the more they often that they collide, the more they're going to increase their pressure and stuff like that. So again, this is just to give you a context or an idea as we start pursuing this particular thing. So if you have questions, let me know.